Other one is December the 5th. All right, let's do this. House robber again. House robber number 3. I think we did number 1. Probably done number 2 as well. I don't remember about number 3. Number 3. Yeah, the one that we did before was you cannot rob the house adjacent to you, and we solve it by dynamic programming. I should have opened it earlier. I have already prepared the second round. Alright, so yeah, we've done this before. I liked it, which means I've done it, but I don't remember when. Sometime last year, most likely. The thief has found himself a new place for his thievery again. Yep, that's last year. Ooh, it was tough. That was tough. A terrible solution, and then I learned a better solution. Okay. Wait, what are you doing? I'm gonna go to description. There is only one entrance to this area called root. Besides the root, each house has one and only one parent house. Each house has one and only one parent house. After a tool, the smart thief realized that all houses in this place form a binary tree. It will automatically contact the police if 2 directly linked houses were broken into on the same night. Given the root, return the maximum amount of money the thief can rob without alerting. So basically it means to rob this, this, and this, right? So instead of doing it on linearly, now we turn it into a binary tree. So I can rob 3. Wait, hold on, let me read again. 2 direct linked houses were broken. So if I rob 3, I cannot rob these 2, but I can rob all these. This gives us 8. Oh, very interesting. Okay, so basically we do this DP in the tree version. So it will be the same. So we do DFS, right? We're going to DFS, traverse the tree, and each time when we hit a node, we're going to ask ourselves, should I rob it or should I not rob it, right? Let's say if I rob this, then I cannot rob the nodes adjacent to me. So I cannot rob my parent, nor can I rob my children. So when I go, I need to pass my parent and myself, right? Okay. So if I want to rob, then I cannot rob my parent. Oh, when I cannot rob my parent, then who am I going to contact? My parent's parent? Oh, exactly, my parent's parent, right? Like if I rob, like I say, I rob 4, then I cannot rob 3, right? So my value does not come from here, the maximum here. The value comes the maximum that my parent's parent can obtain, right? Parent's parent can obtain, and since each house has only one parent house, right? So from this is my parent only has one parent house. And in this case, its parent house is nothing. So We can actually add a dummy node to this. This parent house value will be 0, right? So if I want to rob 4, then I say I'm going to check my parent, which gives me 0. So that will be the maximum value I can get if I rob 4, which is 4, right? 4, oh yeah, and then from 4, since I robbed 4, hold on, I don't have to. Because if we're doing it as a recursion, right? I say if I rob 4, if I can rob 4, that means I must have robbed the parent of the parent, right? If I rob this, then I know I cannot rob my child, so all my children cannot be robbed. So to go forward, hold on, there are two ways of thinking, right? Two ways of thinking. Say, if I rob the current node, then I can actually direct the next robbing. So I will go to all my children, which none of them I can rob, and I will rob my children's children, right? So once I rob my children's children, that already means, so once a node is robbed, that already means my parent's parent has been robbed. Okay. Again, so for each node, if I visit a node, is that the right way to think though? Is that the right way to think? So I'm at here, said I want to rob my child. If I want to rob 3, right? I want to rob 3. Let's simplify the problem. If I have one node, right? Either rob or don't rob. If I have 2 nodes, so at a parent, I can say, oh, I want to rob the parent. Well, it should be like how much money? What's the maximum amount of money I can get, right? If I rob my parent. I shouldn't, no, hold on. The original question is, at this position, at this house, the maximum I can get at this house, right? Whether I rob it or I don't rob it, it doesn't matter. I just compute the maximum I can get at this house, right? The current house. And the maximum I can get at the current house will be contingent on all the houses I visited before, but not on all the houses that will be visited later, okay? So at the root, it will be 3, because the maximum I can get by robbing this house is 3, right? Now I have 2 children, 3 have 2 children, so now I'll visit one of the children, right? So for this children, I have 2 choices. One is I want to rob it. Now if I rob it, then I cannot get, then I need to find my parent's parent, right? And to find the worth, the maximum that my parent's parent can get. And my parent's parent is 0, so if I rob myself, the max I can get at this point, right? At this point in time, because everything, each subtree is linear. Hold on. I think I'm conflicting 2 ways of thinking. Let's change it, right? So what we're asking is, at this point, at the root 3, right? I can either rob 3 or not rob 3. And then there are 2 scenarios will affect how the remaining will work. And if I rob 3, then I'll have a way of computing. If I don't rob 3, I have another way of computing, right? And the 2 ways of computing, put it together, and that will be the maximum I can get at this position, and that's the value we want, right? That's the value we want. Okay, so if I rob myself, right? Then I'll have value 3, but then I cannot rob all my children. So what I'm gonna do is the next we're gonna visit is my children's children, right? My children's children. So I'm gonna go visit my children. Let's say can rob, cannot rob. If I cannot rob myself, wait, so what do you mean? Like when I pass it, I'll have a value say can or cannot rob. Or at each node, I will always visit my children, right? So for the root, always visit my children. The children will return 2 values. Okay. What about the children return 2 values? One is the maximum that happen if the children is robbed, and the other is the maximum if the children is not robbed. 2 values, but we don't combine them, so we return 2 values. So if we return 2 values, then I can check, right? So if this one return 2 values and this one return 2 values, then I can check. So based on this, if I draw it out, this whole tree, right? So for every node, I am going to visit my left, visit my right, and they're gonna give me 2 values. One is the maximum we will get by the child being robbed, and the other is by the child not being robbed. So if we go down, and if it's a leaf, right? If it's a leaf, then we're gonna return 2 values and called getting robbed. We're gonna return 1. And not robbed, like if I here I do not rob it, then it's getting 0, right? So 1 0 will return. So at this 4, right? At this 4, on the left side what we get is 1 0. On the right side we get is a 3 0, right? So in that case we say, which means now for 4, if I rob 4, then the maximum value I can get is 4. So if I rob 4, maximum value is 4. If I do not rob 4, then the maximum value I can get is 4. So 4 will return 4 and 4, right? 4 will return 4 and 4 to 3. And with 5, we don't have a left, we won't have a right. So if I don't have a left, which is a none, none will just return 0 0. So on the right, we'll return a 1 0. So it's a 1 0 and a 0 0. So again, if I rob 5, I'll get 5. If I do not rob 5, I'll get a 1. So this is return 5 1. So this is what 3 sees. The 3 sees 4 4 and 5 1. So the 3 says, okay, if I rob myself, which will give me 3, then I can get 4, because on this side, and then not rob is 4. On this side, not rob is 1. So it'd be 3 plus 4 plus 1, which gives me 8. If I do not rob myself, then I can rob 4 and 5, which will give me 9, right? Therefore, from 3, when it returns, it's going to return 8 and 9, and I will just take the maximum of the 2, which is 9. I think that is the case, so let's code it up. I have high hope for this because it's simple, very straightforward. We do still have to use another one. Let's call it helper. We still need a helper function for this. I have a node, which is going to be optional. Tree node is going to return a tuple, right? Tuple of int and int. Actually, I started like this, so I'm going to use Name tuple. Named tuple, right? Oh no, I can still return int and int, even if it's a name tuple, right? So we're gonna say ret is a return equals name tuple ret, and the two values is gonna be Rob and Rob and not Rob. Ah, sounds weird, but that's fine. So if not node, all right, we're gonna return ret is 0 and 0. Otherwise, we're gonna say left equals helper, no dot left, right equals helper, no dot right. And I want to return ret. Now, if I rob myself, then I'm gonna get no dot val plus left dot not. We just say yes and no. Yes and no. Yes means rob, no means not rob, right? So you say left dot no plus right dot no. Otherwise, if I do not rob myself, then we're gonna say left dot yes plus right dot yes, right? So we're gonna return helper root, and we can take the maximum of this. Okay, it's a tree, so I don't want to run test cases, so we can try this. Let's use both sample test cases. Try it. Wrong answer. What is this? Tree visualizer. Oh, jeez. Okay. Output 6, actually 7. Okay. So 4, 1, 2, and 3. How? 4, 1, 2, 3. I picked. Oh, I think I see why. So my scheme would say 4 plus 2. So my scheme will return 4 plus 2 or 1 plus 3, but actually it's 4 plus 3. Hold on, let me think. So from 4, I say left or right. Now right is nothing, so it's always going to be on the left. So I'm going to say, check 1, so we go all the way down, right, to 3. So 3, it's going to be, if I rob 3, right, it's going to return 3, 0. And for node 2, if I rob 2, then I'm going to get 2. If I don't rob 2, I'm going to get 3. And at a 1, I say, if I rob 1, then I'm going to get, if I rob 1, then I'm going to get 1 plus 3, right? I'll get a 4. If I don't rob 1, if I do not rob 1, that means I can rob 2. And if I rob 2, I get 2. And then 4. Okay, so where's the problem? At 2, that's correct. If I rob 2, I can only get 2, right? Because I cannot rob 3. But if I do not rob 2, then I can get 3. So the 2 is correct. The problem is a 1. If I rob 1, then I cannot rob 2, but I can rob 3. which gives 4. That is correct. But if I do not rob 1, I shall not get 2, but get the maximum of 2 and 3. Right? If I don't rob 1, that means I'm free to rob 2 or 3. So if I don't rob 1, I shall rob the maximum of this, which means the maximum. So when 2 returns 2 or 3, which is the possibility of robbing 2 or not robbing 2, which means if I do not rob 1, then it doesn't matter. It does not matter if I rob 2 or not rob 2. So I shall take the maximum of this. Therefore, for 1, I shall return 4, 3, which means if I rob 1, then I do 1, 3. If I do not rob 1, then I do the maximum of this one return, which is 3, right? So it's 4, 3. Now go to 4. If I rob 4, right, then I cannot rob this, so it's 3. So that's going to give me 7. If I rob 4, that can give me 7. If I don't rob 4, right, then the maximum I can get is 4, right? If I don't rob 4, that means I can rob 1 or do not rob 1. If I rob 1, I get 4. If I don't rob 1, I get 3, right? So total is going to be 4, so therefore it's going to be 7, which means we only need to change one line, right? Only change one line. So left, right, so right. This is if I rob. Right? If I rob, then no-brainer. The left is no, right is no. If I do not rob, right? If I do not rob, then it's going to be the max left plus max right. Because I do not rob myself, so it does not matter if the left or the right is robbed. So in this case, if I do this, I think we'll pass. Yes, and let's run all the test cases again. Well, not all the other test cases. There we go. All right, try it again. We got it. So yeah, I'm pretty sure that is the actual solution, but we're gonna just take a look at what we had in the past. It's an improvement, right? It's an improvement because the first time when I tried it, actually I'm curious what type of solution I had back then, and it was pretty bad. But now, what do you think the speed is because of the name tuple? It could be. So this one is not right. Yeah, it's going to be max left and plus max right. Now speed in this case is, now what's the difference between 48 milliseconds and 64 milliseconds, right? It's not like a bragging right. Once I start using name tuple, I just love it. I just think this idea is great. Right, the ability to call each element in a tuple using a dot notation is tremendously easy in terms of writing code that's maintainable. Like in here, I don't even need documentation. For this one, immediately yes. Oh, okay, that means yes to rob, and no, I mean I can even make it more explicit. And then when you write a code, you don't have to do very cryptic, like left 0, right 1, like that. I can just say dot yes and dot no, and immediately I know the result. Okay, so let's take a look at the good solution we had back then and compare that to what we have today. Oh, cache. Oh shoot, maybe because cache? Yeah, that's exactly the same method. I hold on. Do we cache this? No, we don't have the cache because every node is visited once. You visit every node once. It's a DFS. There's no need to cache. The cache is not the reason. Maybe it's because it's not using a named tuple. But take a look at this one. I'm just curious. Can rob root the val. Oh, I say can rob. Game 2 is self.rob left, and after that, so it's the same idea. This one, oh, I have cache, but still slow. I think it's because it bifurcates too much. Or are we doing repeated work? So basically we're calling, so it doubles, right? It doubles the amount of work. So we have to call same node with a true or with a false. Huh. I don't know, why this one is so slow? Same test cases. Yeah, I think it's because they have to do the same recursion twice, right? We've done it once here, we hit everything, and then we have to hit everything again, but this time, even if you cache, everything is visited uniquely, right? It's visited uniquely. I think that's why. But anyway, so this one does hit the sweet spot. Yeah, so take a look. So anyway, we can write it. So I see improvement in this, right? Which number is this? Oh, not a number. 300 something. I'll worry about it later. So anyway, I have seen improvements in this one. This is the correct solution. However, I did hit a little bit obstacle when one of the test cases failed. The problem was that when a current node is not robbed, right? We do not have to rob its children. In other words, the max profit from not robbing the current node should be the max profit of its children, regardless of whether the children are robbed or not. This is ON. Oh, I think I clicked on the wrong task, but it still is 124, so nothing changed. But anyway, we hit a 64 milliseconds, right? This one has a 29%. Okay, so So that's that. That is that. I'll take a peek at the number of it. 337. 337. Okay, let's roll the other one. So we've done this. And what do you have here? So the next one is called a wiggle sort. Whatever that means. A wiggle sort. Wiggle, wiggle, wiggle. Wiggle sort. Maybe next time I should open it first. Alright, we're already doing this, why not open it? Just put it there and say, okay, this is the next question we want to solve. Yeah, I think I should do that. I can save some time, save these waiting time. Like I'm on the go, my mind is ready, but I just put into a break like this. It's not what I want. Alright, given an integer array, reorder it such that, that is the wiggle. Num0 smaller than num1, larger than num2, smaller than num3, larger than num4. Okay, so that's the number. So 1, so a small, big, small, big, small, big. Small, big, small, big, small, big. Small, big. To check is very easy, right? So small, big, small, big, small, big. Alright, here's the challenge. Do it in ON and in place. And or in place with O1 extra space. 5,000, no, 50,000 values. Okay. Wiggle it. 151164. How do we wiggle this? I mean, So 151, and then we hit. So we need something bigger than 1. How do we look for something bigger than 1? So I put a pointer here, which require a value bigger than something. And keep going, so this, and then the next point, and then we check, say if this is bigger, then we swap. So after swap, remove this, check, it's good, and it's good. Then we're done. We get 151614. It's accepted. I don't know, is this idea legit? So small, big, small, boom, we hit. So this one, now we require something bigger than 2. So we keep going, we have, so now we swap. Right, so we swap, so this one's good, so we keep looking. Small and big, we need something bigger than 1, but no, we cannot do. So if we cannot do, we're backtracking. We're backtracking to the swap, which means it cannot swap that way. Then what? Oh, yeah, what did we fail? In the non-ON time, I can always sort it, right? If we talk about just solving it, right? We sort values first. So 1, 1, 2, 2, 3, 3. We sort it first, and then what? And then so 1, we need something big, something small, something big, something small, something big. Therefore, we can just take all the even values, right? All the odd value out, and then take all the even value out, and then odd value out and even value out. No. No. What are you doing? So give the number of values, right? And then we take half. Yeah, exactly. We take half of them, right? Now we take half of them. Well, if it's even or odd, it doesn't matter. Doesn't matter even or odd. If it's even number, we take half, and the other half we just insert in between, right? Because the second half, they are all larger than the first half. So we just insert them in between 1, 2, 1, 3, 2, 3. That's it. 1, 2, 1, 3, 2, 3. 1, 3, 2, 3. Yeah. And if it's an odd number, then we take the last value out, and then we do this swapping, and I will put the last value to the front. Actually, we can take the first value out. No, wait. So we can take. Let's see, how can we swap? This is O1 log n, but well, I think I'll that's more than just a swap. It's insert in between, and then that's not O1 extra space. We basically create two arrays, right? And then we're gonna just insert them 1, 2, 1, 3, 2, 3. If I have another value, then we can put. It's gonna be a big value, right? So it'll be hard to put. So we're actually gonna take the small one out. We'll take small one out, and the remaining we get it and put the small one at the end. We can solve this in. Yeah, let me first solve it. That'll be simple, right? If we don't have these restrictions. Yeah, we can think about the restrictions as we go along. But right now, I just want to solve it first. Maybe by doing this, something will hit me. Oh, hold on. They say do not modify anything. Do not return anything. Oh, shoot. That's fine. We just copy. That's stupid. That's very stupid. All right. Let's see if we can do swapping. So if we do swapping, how can we do swapping? Well, we can, right? We can if we take first half out, and then the second half we'll just insert into even positions, right? Which is insert into even positions. No, actually not even positions, odd indices. We insert into odd indices. No, wait. We insert into even indices. Well, it depends. It depends on the length. So we insert into these indices, and then we insert the smaller value into the bigger value into even indices, and the smaller value into odd indices. And once we've done that, yeah, we can do that. Yeah, we can do that. So we have to copy, right? We have to copy the entire thing. That's unfortunate. But said we are going to just solve it. Basically, we say sorted nums, right? Sorted nums equals sorted nums, right? And then based on whether num is even or odd, we're going to take, if it's even, then we're going to take the indices. So we're going to put the small values in first, okay? So the index is going to be the end, let's call it value, let's call k equal to len nums, right, divided by 2. So 0, 1, 2, 3. Right, if I have 6 values, 6 divided by 2 is 3. So 0, 1, 2, 3. That's the starting point of the second half. If I have 7 values, 7 divided by 2 is still 3. And that is not the starting point of the second half. We want the end point of the first half. Well, which is the starting point. So we do have to do this. So this, if let's also do this. N equals len nums, right? So we say k equals, oh, shouldn't we just say this plus 1 divided by 2? Well, then k equals m plus 1 divided by 2. So if it's 6, that's 7. Divided by 2 is still 3. That's good. But if it's 7, that will be 4. 0, 1, 2, 3, 4. Right? That'll be 4. Okay. So in that case, then we're going to say position the smaller values. Let's say for I in range. Now this is important. Either from 0 to, so we say 0 plus n, right? So if n is the even number, then we go from 0. If n is odd number, then we go from 1 all the way to k. Right, and then we just say nums I will equal to sorted nums what? Well, actually equal to sorted nums I, but that's actually not I. We do need a j, right? And then j will start from 0. J will always start from 0. And after that, j will plus equal to 2, right? So we go through this and then position the bigger values, right? The bigger values, j is going to be 1. And for I in range, that's going to be from k to n, right? And then we say nums j equals sorted nums I, and j plus equal to 2. So after that, what we're going to say is if n is the odd, then we say nums minus 1, the last value, will equal to sorted nums 0. That's it. Okay. Oh, how do we do this in the required. Interesting. Oh. There are so many different solutions. So therefore, what we want is just a bunch of tests. Okay, so all we want is tests. There's no answer. The answer is created by checking, right? By checking. So we're gonna check the answer, but not really to equal. So we're just gonna say for nums, right? And this is gonna be wiggle nums. How do we check? Oh, we check by first smaller than second. So say correct is true, and we simply say for I in range 1 to len nums, right? Say if I is at odd position, the odd position will always be bigger, right? So if this and red and nums I is larger than nums, and nums I minus 1, if this or, so that's one condition, is at odd position, or at even position, I is 0, right? And if it's even position, then nums I is smaller than nums I minus 1. Right? If it's even position, then we'll continue. Even position must be smaller than the previous one. And else correct equals false. Break. And then we say if correct, then pass, otherwise fail. Okay, so we run this. False path. And we can just try this one. I mean, this will work, but you have to still think about. Wait, did I click it? Yeah, I clicked it. Oh, wrong answer. Oof. Even with this, it's still not correct. We need to prevent the same 4, 5, 5, 6. All right. The answer is not defined. Oh, of course, yeah, fail. Oh, I also have no rest. Rest actually just nums. Okay, so I cannot do this insert, so I need to reverse it from this one insert, right? Because this one's definitely not going to be the same as this. Okay, and if we insert this the biggest, insert the smallest, and right as we go in towards the end, so this will be what, 4, 6. This will be 4, 6, 5, 5. Oh, that is still not right. So 4, 5, and 5, 6. Man. Oh, this this will answer is 5, 4, 5, 6. Whew. Turns out this is actually not. Yeah, I'm gonna give up. But this is not part of the requirement anyway, so I'm gonna rethink about this. So let's say 5, 5, 6. Okay, let's try dynamic programming. If I have only one value, we just return it. If I have two values, we just return it, because they say every problem has guaranteed there will be an answer. So if it's two values, we just return it. Okay, no, actually not. If two value is like 5, 4, we have to return 4, 5, right? So if it's two values, we need to check if the first one is smaller than the second one. If not, we need to, if it is, we return it. If not, we need to swap it. Okay, that's two values. How about three values? 4, 5, 5, right? 4, 5, 5, three values. And we check 5 and 5, equal. So there are two choices, right? In this case, I have two choices if it doesn't work. One choice is, well, actually we don't have a choice in this case, because there will be nothing bigger than 5. Oh, there will be, actually, if we go, hold on, let me think. So when this happens, when it's not right, that means I have some value which is larger or equal to the immediate previous. So it's not right. So we need something smaller. Okay, so we need something smaller here. Now, what we do know, something smaller, is the value in front of me. That value is definitely smaller than me. So if I want to swap this value to here, okay. So let's say if I have two values which are adjacent, but the second value is larger or equal to the previous one, then we can solve this by moving this one in between these two. Remove which value? Remove some value that's smaller than the previous one. Move it in between. If it's three values, yes, that is the solution, right? So three values, I can swap the first two so they are correct, and the third value comes in. If the third value is smaller, we're done. If the third value is bigger, then we move the first value in between the two. So 5, 4, 5 will become 4, 5, 5 become 5, 4, 5. Now we hit a 6 and 5. Oh, 5, 4, 5, 6 is not correct. All right, this one shall be. Wait, hold on. No, hold on. No, I don't want to see discussion. I do not want to see discussion. I'm just doing the process. What's the correct answer for 5, 5, 4, 5, 5, 6? 5, 6. It's 5, 6, 5, 4. I think that's the one. 5, 6. No, 5, 6, 5, 4 is not correct. Expected 5, 6, 4, 5. 5, 6, 4, 5. 5, 6 go up, 4 go down, 5 go up. Yeah, 5, 6, 4, 5. Okay, but so 4, 5, 5 will not have a solution. Oh, damn. 455 will not have a solution. If we do not have a solution, why we do not have a solution? Because 5 is something big, and now we have 2 big values and 1 small value. Right? That's not possible because for 3 values to work, we must have 2 small values and 1 big value. So this one doesn't work. When I add 6, okay? Add 6, that means we need a small, small, and a big, and big. But the big is only relative to the small. Okay? So we have a small, big, and a small, big. That doesn't work. Small and big. If we sort, let's go back. If we sort it, right? If we sort it, we do produce pairs of small, big, but there will be duplicates. Big values, right? Big value. 5 and 6 is big value, and the big value do take the big position. Small value take the small position. So big value, if we take the big position, only the small value in between. Oh, that is only one solution for this. Yeah, how do we solve 4, 5, 5, 6 programmatically? Five and 6 and 4, 5. A pair. If you think about it, it's like pairs, right? We're doing pairs. We can move as unit of pairs because what we have is what we want is a small, big, small, big, small, big, right? Small, small, big, small, big, small, big. So each small, big can be a pair. Each small, big is a pair. So all we need to make sure is the big one is always larger than the small one between pairs. So say we sort an array, right? And we can produce pairs. Okay, we can produce pairs. And after producing pairs, it doesn't matter, we're just producing pairs. Wait, it does matter. The pair has to be, the first one needs to be small, the second one needs to be bigger. Okay? So if there are values that are the same, then they cannot be paired together. Okay? Now we have pairs. Yeah, it could be like this, right? Pairs. And then when we get a pair, now we need to move them around. We can go the last pair because the last value then front value, this and this. What if I have 3 in a row? Guarantee there will be one answer. I can't even solve 4. Like this 4, 5, 5, 6. I can't have a good way to solve it. What if we break into half? Now I have 4, 5. So 4, 5 is right. 5, 6 is correct. So we'll have both pairs are correct. Now if both pairs are correct, we need to put it together. We just need to make sure they're either left to right or right left, and then we just pick one way to make it work. Now if we go left and right, then 5 and 5 doesn't work. But if we pick the other one, it works. So now we're going to go 4, 6, 5, 4, 5. Okay, that will work. Are you saying we're doing this divide and conquer? 1, 3, 2, 2, 3, 1. That's the 2 part, right? But that's 2 part. That's 1, 3, 2 works. 2, 3, 1 works as well. Then what? 1, 3, 2 works and 2, 3, 1 works. They're gonna swap. They cannot swap. And then come back. We know 2 and 2 doesn't work. So we reverse, so 2, 3, 1, 1, 3, 2. It doesn't work as well. What are you saying? There has to be even numbers. Like if it's odd number, it's okay. Even numbers, so we do what? So instead of 1, 3, 2, 2, 3, 1, we do 1, 3, 2, 2, and 3, 1. Okay? So that's the first split, 1, 3, 2, 2, and 3, 1. And 3, 1, we can solve it. This one is going to return 1, 3. 1, 3, 2, 2, we keep splitting. So it'll be 1, 3, and 2, 2. 2, 2 never works, so we cannot do 2, 2. Yeah, what if we have like 2, 2, things like that? Well, in that case, let's say we'll swap, right? We'll just swap with anything. How can we make sure that one swap will break it? What if we say let's say we don't, just like 2, 2. So 1, 3, and 2, 2. So 1, 3 we can do, 2, 2 we cannot do, but it doesn't matter. Now we're going to merge. Now 1, 3, and 2, 2, how do we merge? Now, if the 2, 2 is also a good pair, then we can say either we do this or we go back and forth. But now 2, 2 is not a pair, right? It's not a pair. So in order to work, so 1, 3, 2, 2, in order to work, we need a small, big, and a small, big. So 1, 3, does it 1, 3, 2, 2 even work? Yeah, it can have 1, 2, and 2, 3, right? And we can do 2, 3, 1, 2, small, big, small, big. Yeah, 2, 3, 1, 2. But that requires we swap. break, because it's the same value. It's the same value. So we have a small, big, and we have another one is the same value. What if we don't have a solution for 4 values? Or are we always going to have a solution for 4 values? Unless they're all the same. Unless they're all the same. How about if it's 4 different values, we can always find a solution. If 4 values, we have repeats in them, right? If we have repeats in them, then like 4, 4, 2, 2. How about 4, 4, 2, 2? 2, 4, 2, 4. That works, right? 2, 4, 2, 4 works. Like 3, 6. How about 2, 2, 3, 6? Well, 2, 2, 3, 6, we can break into 2, 3, 2, 6. And then 2, 3, 2, 6 works. That means as long as we can break it open, and we can just keep doing this until we go to the 4 stage, right? So now we have 4 values, 1, 3, and 2, 2, which is 4 values. And we just simply need to break it, right? How do we break it? Now, because these two are the same, so I can just break it like this. What if we have 3 values the same? Then it's not possible. And they can also put 3 values the same. If 3 values are the same, or if 4 values are the same, then we're talking about if 3 values are the same, then it's to have 3 consecutive values. So we can just first go through, if 2 values are the same, we can, hey, how about this, right? We go through the entire thing, and if we find repeats, we simply swap, right? So we just constantly looking for repeated values. So in this one, 1, 3, 2, 2, 3, 1, right? We say 2, 3 is not the same, okay? And then 2, 2 is the same. But I know 2, 3 is not the same. So I just swap 2, 3, swap the previous. And then if I have consecutive, then I'm going to swap these, right? Same. And these are not, oh. Hold on, I'll be back. Yeah, I just realized it could be a case of say 1, 1, 1, 1, and 2, 2, 2, 2. The answer will be 1, 2, 1, 2, 1, 2, 1, 2. But it will be very difficult to do because everything is consecutive. So what I'm looking for is to break the consecutive. Okay, let's loosen it. Let's sort it first. If I sorted it and we have consecutive, we simply swap with the largest. So we compare. So 1 and 1 are the same. So we basically say the current value I will swap with the largest value. Okay, I swap with the largest value. And now 1, 1 is the same, and we swap with the second largest value. Oh, I cannot swap with the second largest value. I'm going to produce repeats again. The whole point is trying to break the repeats. Still not satisfactory, yeah? Or put it another way, if we can make every pair a different value, if we can make every pair a different value, then we can do this. All right, we can do this. Every pair into a different value. How can we do that? Make sure every pair is a different value. Well, every pair So if I have consecutive, so we just set up another pointer to look for the first one that's not the same. So we're going to swap. Okay, and now keep going. So these two the same, so we'll go this one. Keep looking the first one not the same, we're going to swap. And then we're looking these two are the same, so if you look at the second one, it's not the same. Swap. Okay, so now all the pairs are not the same, right? Because they said at least one solution exists. That means we can make it into pairs, 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 pairs. They are all not the same. We don't even care about the size, just they are not the same. And then we're going to run our algorithm. Right? Right, then we can run the algorithm by splitting. Now in this case, then we have even numbers, right? So we split and a split and a split. We split into fours, right? Split into fours. And into 4, we just check. I'll split into 2, right? And then into 2, we're gonna order them. come back together. So come back together, we just compare. Right? If it's good, we're just going to swap. Right? We're going to swap the two. Basically just saying these two will point in the front of the other two. What if we have a giant bunch and a giant bunch? Now we want to swap. Like within each, it's all good. Right? Within each is all good. And this is supposed to be larger than this, but this should be larger than this. But now this is smaller than this. Then all we need is to find a pair, right? Find a pair within that allows the front to be smaller than the previous one. Like each strip, I can follow this. Each strip I follow this. How do I merge the two strips? Well, if this is good, then we can merge it directly. If it's not good, if these are not good, like this one's too big. It's a big one. Let's still follow this. But in that case, what do we do? A big one. A big starting point. Well, if it's big, if something is too big, we should always throw it to the front. So we can swap this with the front. Not really swap it with the front. Oh, this feels just convoluted. Very convoluted. Yeah, my original idea was not right, because it's not the smallest to occupy these positions. Talking about relative. Okay, 1, 3. So 2, 3, and 2, 1. And 1, 2. Now we have these. We need to order in such a way. So they are all good. They're all ordered within themselves, right? Then what? Then we need to order based on pick the one that has the largest X3 has the largest, so I say 1, 3 comes out, because that allows me the most possibility to add another one. So if this is the largest, 1, 3 comes out. Now the remaining, I should find the largest. Then 2, 3 comes out, and 1, 2. So 1, 3, 2, 3. So 1, 3, 2, 3, 1, 2. So this is after, right? After we have turned the entire thing into pairs, and then I throw them into a priority queue, and every time pop out the ones with the largest second value, which in a sense, how about we pop out with a smaller first value that can serve at the end, right? Smaller first value, and then popping out the smaller first value, 1, 2, and popping out smaller first value, 2, 3, 1, 2, 3, 1, 2, 1, 3. Okay. 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 But then that's like append front. We can use deck. Right? We can use a deck to append to the front. Yeah, I can do that. Use a deck. And I will always append to the front. There'll be minimum change to the tuple. Or we can just 3, 1, right? So bigger at the front, and then we just come out 1, 3, and append. Now we can append to the front. That's fine. And then once we're done, we just rewrite nums. Okay, so this is a stupid way to do this, but so the first one is we need to break it, right? I'm not sure if this method will work to break the whole thing into pairs. Yeah, it definitely will. It definitely will. We just need to break it into pairs. Okay, how am I supposed to do this to break into pairs? It doesn't even matter how we break into pairs. Hold on, let me think. Oh, what about the even or odd? Even or odd? Jeez. That's fine. That's fine. We're gonna break into pairs, and the last value we just don't consider. We arrange the previous values, and the last value we will know where it goes, right? So if it's a big value, it goes to the front. Cannot go to the front. So we need to take a small value, right? Take the smallest of the values. Take the smallest value because we cannot go to the front. So take the smallest value that will always stick to the end. So we need to sort it first. So we sort it, and then we pick the pairs. We sort it, and then we take pairs. If we have the same, then we swap with the biggest. Right, and then we pair to the end. And now you have pairs. Then we throw all the pairs into a priority queue. Yeah, this is going to be very, very complicated. We are going to use deck. I want to import heap queue. And I want to sort with the nums.sort. Right. Then min n equals nums 0. Well, depends. Depends if we need. So we're gonna say the starting value. Okay, and then as we build up, that doesn't. Okay, it's fine. It's fine. So we're just gonna say for I in range. Okay, n equals len nums, n 2 all the way to n actually minus 1, right? Hold on. No, all the way to n. Wait, no, all the way to n minus 1. And I'm currently at I, so I need to check. Oh, we also need a heap, right? So now I am at I. We say if nums I is not equal to nums I plus 1. Right, if these two are not the same, I'm going to do this. If this is smaller, then heap q dot heap push heap. I'm going to push in nums I plus 1. Right, actually we're gonna go this. Yeah, let's push a tuple. We can push a tuple. It's fine. We'll push a tuple. So I'm gonna push this in, right? We say elif nums I is larger than nums I plus 1. Then we push in the tuple with reversed. Right? So that's now we push in like this. Else, if they're the same, then nums I plus 1, right, or equal to, and then nums, we change with the last one, equals nums minus 1 and nums I plus 1. We swap with the last one, and then this will push in. What would happen that the last one is the same as what we have right now? That would be very unfortunate. No, I don't think so. I think I can swap with the last one. Yeah, we can swap the last one. Oh, oh no. We're gonna find the first one that's not the same, and then swap. So I cannot do that. And I think it'll be easier to control if I use a while loop. While I is smaller than n minus 1. And do this, right, do this, and else. Well, else they're the same, then I'm gonna say j will equal to I plus 2, while j is smaller than n. Right, so just keep going to look for the first one. While j is smaller than n, and nums j, right, is not equal to nums I. Well, actually, when j equal to nums I, then j plus plus. Once it comes out, what if everything is the same? No, it cannot be, because there gotta be one solution, right? And once we find the j, then we do the swap, right? We say nums I plus 1 and then nums j will equal to nums j and nums I plus 1. It feels like looks like we can do this at the very beginning, alright? So j is the next value. The next value, and if the two values are the same, keep going. So we find the first j that is not the same, and then we swap that with I plus 1. And after swap, we say, because if the next one is already not the same, then we can still swap. The swap is just the same as itself. And we can do this. I can say if this, and this one can be else because they are not the same. All right? And then I plus equal to 2. And then in this case, I can use a for loop then. I in range n mod 2 to n minus 1, 2. And then we do all this, blah, blah, blah. Once we're done, we break out. The heap is ready, right? The heap is ready. So we can just say while heap, right? While heap, and we're gonna say the rest need to be. Oh, I don't have to. We're just adding the value into. Hold on. Now we get all the value out, and then starting from this, we just add them in because we pop out as the smallest, right? But every time we pop out will always be the smallest so far. And then we can just fill them in, and yeah. Okay, so while heap, we're gonna pop out, say a and b will equal to heap q dot heap pop heap, right? So pop out a and b, and we need I again. So I will equal to n minus 1 minus n do this, right? If it's even, then that's a 0. We just start from the end. If it's an odd, then we do one more. Okay. So in this case, we're going to say nums I minus 1 nums I equal to a and b because they're sorted, right? And then we push out the smallest, the main heap. So a is the smallest. Therefore, the next time when we pop out, the back will definitely be larger than a. So we do this, and I minus equal to 2, right? And then go up. Once we're done, and we just say if n, if it's this, right? If it's this, oh, we're missing the smallest value. So we sorted it, and then we push everything in, and we need to get the smallest value. A temp equals nums 0. All right, we'll just get it. This is for use when n is odd. And if it's odd, then we simply say nums minus 1 will equal to temp. Otherwise, this one already filled everything. And that's it. Let's try it. Oof. Index out of range. Where? Here. So J is at the end. How? Oh, because we have 3 and 3, right? So we sort it as 1, 1, 2, 2, and 3, 3. So 1 we saw we're going to swap with the first one, so it'll be 1, 2. 1, 2, 3, 3, then 1, 2 go in, 1, 2 go in, and I have 3, 3. Ah, that is not good. How about we don't sort? Oh, if we don't sort, then we don't know which one is the smallest. We still know which one is the smallest. But if we don't sort, they can give me 1, 1, 2, 2, 3, 3. What you gonna do? The same. Okay, the same, and then swap with the last one. Okay, let's do another type of a swap. Let's say they always swap with the last value. Hold on. All we want to do is to make sure that we do not have duplicates, right? What about if we put them into a counter? 1 is 2, 2 is 2, and 3 is 2, right? If we put them into a counter, then let's say I can take 1 and 2. What do I do if I'm using a counter? Then I can sort them. To a counter. Can I shuffle them? Right? If I shuffle them, then the likelihood of this happening is low. Random dot shuffle, yeah. Let's say this is definitely not the solution. At this point, I'm just trying to solve it. I don't even care what solution I use. I just want to shuffle. Is it in place? Yeah, it is in place. Okay, so say from random import shuffle. Then why sort, right? We're just gonna shuffle it. Shuffle nums. And then we use this technique to get, and this temp is gonna be minimum, right? Minimum nums. And then we do this. Wow. Let's see if this one passes. Jesus. All right, let's try this. Oh, even shuffle doesn't work. No, shuffle is not the way to go. I cannot do shuffle. Then what? Yeah, the problem is we need to count. Okay, hold on. What if we do counter, right? If we do counter, we can go through counter, right, once, and everybody will be unique, and go through counter again. Let's use counter. Let's use counter. I'm not using deck, but I can use counter, and definitely not shuffle. Come on, man, just stupid. So we say counter equals to counter nums, right? Then I'm going to produce a new list. Now I'm going to produce a new list. I'm going to say not no duplicates is adjacent not equal. That's going to be this. And just say for, right? Let's say for n in counter dot keys, right? And then let's say this dot append n and counter n minus equal 1 if n, if counter and if not counter n, then del counter n, right? And then we go back, so counter change, then we go back to new keys, and we hit, and eventually, I mean, this is a good test case. I should have put that in here. This is a good test case. So this will give us a no adjacent, right? And then this will heap. And this is the same, then we don't have to do this anymore. And all we need to do is check if this, we push this, if not, we push this. Make sure the 2 is ordered. Which actually combine them, right? Okay, combine them into one line, like this. Right, we say he push this, if this, else. We can actually write it, let's write this. I want to say AB equals this, right? AB equals this. And then we say we're going to push AB if A is smaller than B, right? A is smaller than B, else we push BA. Alright, once it's done, we do this, and temp is fine. While heap AB again, blah blah blah, and we run this. Size changed, So we can just do a list because if they want to change size. Say for 1 1. How come 1 1? Jason not equal. Wait, hold on. What the heck? Anyway, this one failed, right? Test 5. Oh, shoot. Okay. Alright. That is not correct. 1 5 6 4. Oh, we have 3 1s. Jesus. One five 6 4. We added and then if not, well, how about this? We hold on. Delete and then come back again. As long as we have elements in, so as long as, let's say, while len counter, right, is larger than 1, then we do this, right? And then we're going to print this and print the counter. That makes sense, right? That makes sense. Once this happens, because we have only one value that's repeated, so all we need to do is just insert that value into any of these positions, right? Any of these positions. How do we do that? We can just do look for any position. We go through them. If any position, the left and right is not, we put this one value in and push this to the end. He has not. Push 1 in, push 6 to the end. I feel stupid. This still feels stupid. How about this? All the same values, right? We just go 1, 1, 1, right? And then that's the same. So we do these, and then we push 1, 1, 1 out, right? So we have a bunch of values which already they are no adjacent equal, And we have the last value with adjacent equal. So we basically just do 1, 1, 1, and we try to push. Now we just try to insert this value into any of these positions. So how about like we have the highest repeat, right? Highest repeat, we do like this. I have total number. I'll have the highest repeat, so we do this. The secondary repeat, so we just fill in the values, right? We fill in the values, and then once we fill in the values, we have more, then we create a new one. Okay, so I have that, so I just do that, and then the second one repeats, we just do from here, so we know the range. This is highest repeat. The second one will definitely be smaller, so we're just filling the blanks. Filling the blanks, and we have the next one, and then the next one we're filling the blanks. Once we're done with filling the blanks, and we add the remaining values to the end. Okay, let's try this one. This one might be easy to do. So this is going to be 0 times n. Right? And then highest repeat. Oh no, that's still not going to be right, because if we have highest repeat, hold on, highest repeat with the second, so the top two repeats. Okay, most common, right? So most common 2, and then they come out, and then we just peel them off, peel them off, peel them off, and then we add it back in. The most common 2 come out, we peel them off, peel them off, peel them off, put them back in. The most common 2 values. Okay, so we pair them up, push them into the, actually pair them up, push them into the heap directly. Pair them up, push them into the heap, pair them up, push them into the heap. And then if there's any remaining, we push that into the counter, we do that again, right? We do that again. And eventually, the counter either go up or we only have 1 left. But in this case, we cannot guarantee the smallest, so we need to so we're going to sort the numbers first, and we do the counter. Yeah, we can sort it. Why don't we sort it first? It just, yeah, so we sorted it first. Still, if we sort it first, then we do the counters for 1 to the end. Right, so either 0 to the end or 1 to the end. And then there'll be no such concern, because there will always be pairs. let's try this idea. So n is this. We say if n, then we're gonna not really. Nums.sort. And then it's gonna be to the end. This is the counter, right? And then we don't need this. So that's the counter. And then we're gonna do counter the most common. So we need Python counter. I think I saw it earlier. Yeah, here. Counter. It has something called most common, right? So we know the two most common. Okay. So do counters this. It's going to be while counter. All right. So the most common, I'm going to say value and count. So A, count A, B, count B equals counter dot most common 2, right? So these two grab out, and then I'm gonna say what? We can zip them. Zip them. Okay, I'm gonna say if count A is larger than count B, right? Then if count A is larger than count, hold on. So I'm gonna keep them out, and then del counter A and delete counter B, right? Then we say if this is larger than counter B, then counter A will equal to CB minus CA. K equals CB, right? If CA is smaller than CB, then counter B equals CA. Oh, hold on, it's CA minus CB. Right, it's going to be counter B minus counter A. And K equals CA. Right? Else K equals CA. Right. So when that's done, I simply say for this in range K, we'll do the heap Q dot heap push. Oh, I haven't defined a heap yet. Right, that's a heap, and then I'm gonna push a tuple. We'll just say same thing. AB if A is smaller than B, else BA, right? And then because I define it again, so I come out, we're gonna keep popping out until deleted. The last one. Yeah, so that shall do, because we handle all the. Okay, so once this is done, we have the heap, right? And then we do also need the smallest. Of course, the smallest is going to be non-zero, because I already sorted it. And the rest shall be fine. Try it. Okay, let's try the others. Ugh. Which one? Not enough to unpack. How? How was it not enough to unpack? Second one? Hold on. Oh, shoot, because you sorted it. Then 3, 2 will handle it, and then we have 1 left. But hold on. This is, no, this is, we have 6, right? 0 to the end. So pop out. Oh, 1 and 2 comes out. Oh gosh. No, it's not right. Yeah, you're right, it's not right. Alright, I give up. I don't know. I don't know how to make that into... How do I make them into distinct pairs? I have a way to order them, but I don't have a way to make them into distinct pairs. Gotta be a way to make them into distinct pairs. Now, that's why I was trying, using counter to make them into distinct pairs. Distinct pairs. These two are equal, right? So that's the problem. If they're equal, then if consecutively I have equal, then what? Then take this one out and try to match to the next one. Just keep going and finding the first one that's not equal. We'll take the pair. But we have issue with this, right? We have issue with this. First one that's not equal. Okay? So they form a pair. Then we'll go back to the start. Now I find the first one that's not equal. Yeah, we'll have issue with 1, 1, 2, 2, 3, 3. That's the issue. Okay, so we find the first one that's not equal. That's going to be 1, 2. And then be 1, 2. Now we have 3, 3. That's why I figured out if we can do like a 1, 2, 3 and a 1, 2, 3, right? That will be much easier. But if we do 1, 2, 3, 1, 2, 3, then we're gonna have a problem with we have some value left over, right, with multiple duplicates. Nah, I give up. I mean, anyway, it's not going to be correct anyway because it's not on and not in place. These problems. Maybe we can go a hint. Do we have a hint? Related topics. Divide and conquer. Selection sort. No, wait, that's quick select. Divide and conquer. Divide and conquer. We thought about divide and conquer. Nope. Give up. Oh. Let's see. Virtual indexing. 3-line. Jesus. 3-line. Virtual indexing. No. First, I find a medium using nth element that only guarantees O and average time complexity. Three-way partitioning. Equal to the median comes next, and those smaller than the median come last. You know what? No, I don't think this is. Let me try to read another one. I just want a standard solution for this. Index mapping. Find kth largest function to get the median element. Assume origin array is this. After you get median element, how do you get the median element? Nums in partially sorted such that the first half is larger or equal to this median and the second half is smaller or equal to the median. We want to put the number in the following. Elements smaller than the median are put in the last even slot. Elements larger than the median are put in the first odd shots. The median are put in the remaining slots. Median I want to put 13, 6, and 5 in index 1, 3, 5, and 5, 4, 2 in 0, 2, 4. Color sort. More and more concept that I have no idea of. Jesus. Wait, how do you find the kth largest? We can sort it to find the kth largest. Alright, I'm gonna read again, but I'll be back. Alright, let's take a look again. Okay, I have a 3-line Python, so I have to read this one as well. Huh? Smaller half of the numbers on the even indices, and the larger half on the odd indices. The smaller half of the numbers on the even indices and the larger half on the odd, both from left to right. The smaller half and the larger half. But it has to be reversed. Oh. Reversed. And the larger half also reversed. I want odd indices are larger than their neighbors, so it's the second half. I have this idea initially too, right? We divide it into two, first half and second half, and then I'm trying to do this, but I need to reverse it. It's because of 5, 4, 5, 6. But this idea didn't work because 5, 4, 5, 6 doesn't work. So So this 5, 6 is the larger half, 4, 5 is the smaller half. So the smaller half has to take, the even position, and the larger half take the odd position. So I've also going to work. So if I reverse the smaller half, it comes 5, 4, and 6, 5. Why does reverse works? Well, the issue is we need to get the end of the smaller half and the beginning of the larger half as far away as possible, right? If we go small to large and small to large, then the end and the end will be together, and then we don't want that. So if we swap the first one, it'll be large to small, then it will be, because we go this, hold on. So small to large, it doesn't work because the largest of the small and the smallest of the large might coincide. Yes, they might coincide. I mean, in regular case, they do not, but they might. Okay, so we want to reverse that, so we go 5 and 4. And then the first will coincide. So the only way to get the big value of the small side and the small value of the big side as far away as possible is to do this. We reverse both. Then this is at the start, and this is at the end, so they're far away. And then it works. And this is in place. Yeah, could they be equal to? S means a small number than m, and L means a number larger than. It's a medium that will cause the problem, right? Because the small and large are separated, so this will never be a problem. We have 2m, that's fine. Quite far apart, yeah. But if we have more, they will be interspersed by L. Number n. Yes, because if n is even, the most we have, because if more than, then there will be a pair. There will definitely be a pair of the same.